So now let's take a look at some examples here where we have two systems of linear equations, one that should be a little familiar and one that's a little bit different, but both 3 by 3, as it were, where we're going to translate these into augmented matrices. So what we're going to do is look at our systems here and we're going to identify coefficients. So let's start with that first one where what we do is look at where the coefficients are. We look at the x values in each equation. Those x values in each equation are going to be what go into the first column of our matrix. So when we're thinking about the construction we're going to end up with, and it'll pop up here in just a little bit, we're looking at something that has a 4, a 2, and a -2 in the first row because those are the coefficients for all of the x values in our system. Or excuse me, column. You gotta be careful with that wording. And then we can go into the next, the y values, and see that we have a 4, a y by itself, so a 1, and then another 4. So our second column is going to be 4, 1, 4. Then we look at the z's. We have a -8, a 3, and a -5. So our selections will go like so. Then we're going to have that vertical line pop up in there to take care of the fact that what we're looking at is augmented, to throw in some notation of equality in there. That's the purpose of that line. And then on the other side, we're going to put the constant terms. And some of you might think to yourself, well, constants are coefficients too. And yes, they are. But for our purposes, we're going to make a little distinction between them. It just makes the relationship a bit cleaner if I generally refer to those as constants rather than coefficients, even though, yes, technically it's not a distinction. But anyway, because the constants are 0, 6, and -3, our last column is going to be 0, 6, -3. And then if we take all those pieces, spin them around, we'll get an augmented matrix like so. And the other way we could have handled dealing with the augmented matrix, the other way we could have handled with constructing that matrix would have been by going equation by equation, that is, taking things in terms of rows. And that's actually what I'll do for the second example here, partially because it's a little bit cleaner with that second one, because that second one's missing terms. But so what we're going to do for the second piece is go through those values, and we're going to see where different things fit. And what's going to happen, and actually I should put this guy up here and keep the old one up there just so you can see it a little bit cleaner. What's going to happen is we will look at the rows, turn them into rows. So we have, for that first equation, x, 3y, -6z, and 10. So the first row will be 1, because there's just one x, 3, because there are 3 y's, and -6, because there are -6 z's, along with, on the other side of the augmentation part, a value of 10. From there, we're going to go to the next row, the next equation, and see that in this equation, we don't actually have any x's. We technically have 0 x's in there. We could insert that if we want to, but generally when we're writing things algebraically, we kind of avoid that sort of redundancy. But anyway, in this case, we're going to have to put in that row a 0 for 0 x's, a 1, because there's 1 y, a 2, excuse me, not a 2. No, there's, jeez, can't read my own notes sometimes. A 2, because there are 2 z's, and then finally a -2 to represent the constant value -2 on the right side of the equation. Now, for our last row, we're going to go through here, and what we're going to do is put in a value of 0, because there are no x values, another value 0, because there are no y values, and then 1, because there's only one z, along with the other side, the constant 12, and then we're going to draw in that line there to symbolize that it is an augmented matrix and not the other kind that we'll talk about later. And from this, hopefully if we're thinking about it in terms of solutions, because that's what we like to do with this section in particular, we should notice that in our first piece down there, before we did any work in terms of translating it, we actually could have worked our way to a solution pretty directly, because that equation there being z equals 13 tells us that we could just directly substitute that value. And because the second equation is just y and z, we could plug it into there, get y, then we have y and z, plug those into there, and we get x, and I actually don't care about what the number is. You can check it for yourself if you want to be sure, but the point is, we could have solved that directly. Well, with a little bit of work. And when we have a matrix in this form, that means we can do that same sort of thing. We can have that same sort of thought. So this construction here, where we have zeros below and then along that diagonal piece, it's called the main diagonal, very suggestive name, we have ones. That's what's called row echelon form. Row echelon form is a specific pattern in matrices where you have zeros on the bottom diagonal half, the lower triangular is what it's sometimes called, and then ones along the middle, and then above can be whatever it wants to be. We only care about what happens in the bottom and middle for row echelon form, and the power of that construction here is that it allows us to work with this thing algebraically. It allows us to do some work to solve the system, actually. Because, thinking about this one, okay, that's cool, we have a place we can go, but that one, we did it before, great, we pulled out some numbers, but that doesn't get us any closer to solving it. However, what we're going to see next is that with a little bit of algebra that you can do on matrices, we're going to be able to take something like that and turn it into something like this, so that we'll be able to get to that solution that I mentioned earlier. But that's what we'll see next.